Hello and welcome to my channel. I'm Emily. Today we are going to be looking at GCSE chemistry, topic 4, chemical changes. So this is all about reactivity of metals, acids and electrolysis. Before we jump in, please let me know. I plan on doing a series of going through exam questions once I've gone through all the topics. Please let me know if this is something that's useful to you, and of course subscribe to my channel if you want to be notified, you want to know when these exam question videos come out. And of course, subscribe, comment below if you have any questions at all. These will either be answered by myself or your fellow students. And feel free to like it as well, because I don't know what difference that makes, but it would be nice to see a few likes in there. Anyway, I'm going to stop talking now. Well, I'm going to keep talking, but I'm going to move on to the actual content. So firstly, looking at reactivity of metals, starting off with metal oxides. So these are formed when metals react with oxygen, known as oxidation. And then we've also got this thing called redox. So this involves reduction and oxidation. So reduction is the loss of oxygen or the gain of electrons, and oxidation is the gain of oxygen or the loss of electrons. When metal reacts with other substances, metal atoms form positive ions, and reactivity is related to their tendency to form positive ions. So you can kind of see here how certain elements react with either water or dilute acid, and in these tables they are ordered by their reactivity. So at the top, potassium reacts the most with water. As you can see, it reacts violently. Whereas, in the table below, you can see that calcium is the most reactive with dilute acid, whereas calcium is the slowest to react with water, and copper is the slowest to react with dilute acid. So a more reactive metal can displace a less reactive metal from a compound. So for example, if copper was part of a compound, then placed into an environment with calcium and acid, the calcium would displace the copper, if that makes sense, to help kind of put into real terms what this kind of reactivity can mean. Most metals are found as compounds that require chemical reactions to extract the metal. Again, you can kind of see here another demonstration of how reactivity works. So essentially, potassium is the most reactive out of these elements, whereas platinum is the least reactive. And you can kind of see, based on their reactivity, how we actually need to work, what we need to do to them to actually get them separated and by themselves. So potassium, to anything above carbon, has to be extracted by electrolysis. Anything between carbon and hydrogen, extracted by reduction. And then copper, silver, gold and platinum are so unreactive that they are actually just found in their native state in nature. You can remember oxidation and reduction in terms of electrons, so aka oil rig. A fun little thing, I swear every subject has at least one of these things where certain subjects more than others, where you have like a little rhyme to kind of remember. So oil rig stands for oxidation is loss, reduction is gain. So I know on the previous slide we spoke about how they are involved with oxygen, but this oil rig specifically looks at electrons, and the electron loss or gain is opposite to the oxygen, basically. So you can kind of see the half equations for how these oxidation and reduction equations will generally look. So oxidation is obviously where the element is going from X to X plus an electron on the side, because it's lost the electron. Whereas reduction is the opposite, so you're going from X plus being joined with an electron to just form X. Remember that charges need to add up and be balanced, so just like any normal equation, you need to make sure that the charges are correct. So like in these half equations, you've got a positive and a negative forming a neutral element on the other side. And an example of how to tell what's been oxidized or reduced. So in this example, we have sodium reacting with hydrochloric acid to form sodium chloride and hydrogen. So in this example, sodium is losing electrons, so I believe that is being oxidized, and then the hydrogen is being reduced. Then looking at reactions of acids. So reactions of acids with metals. Acids react with some metals to produce a salt and hydrogen as a redox reaction. So this is acid plus metal going to form salt and hydrogen, with an example below of hydrochloric acid and magnesium. It's really, really important you remember these kind of general equations so you know what you're doing, what you're writing, and what's being formed. And then you've got the neutralization of acids and salt production. So acids are neutralized by alkalis and bases to produce salt and water. So generally very similar equations, except either alkali or base for this one. Acids are neutralized by metal carbonates to produce salts, water, and carbon dioxide. So acid plus metal carbonate produces salt, water, and carbon dioxide. Obviously, this also makes it a lot easier to work out what the salt would be if you're actually looking at the specific formula, because you know exactly what water and carbon dioxide are made up of, the structure of them, so that can help you figure out what the salt is meant to be. Salt produced depends on the alkali or base used. So hydrochloric acid produces X chloride, HNO3 produces XNO3, H2SO4 produces XSO4. So basically, you're removing whatever is on the beginning of the alkali or base and adding the main component of the acid. It also depends on the positive ions in the base, alkali or carbonate, the charges on the positive ion from the base, alkali, carbonate, etc., and the negative ion from the acid must add up to 0, aka a balanced equation like always. Soluble salts now. These can be made from acids by reacting them with solid insoluble substances, so metals, metal oxides, hydroxides, and carbonates. This is known as crystallization. So the basic process of this, so add the solid insoluble substance to the acid and wait for the solid to dissolve. The acid has been neutralized once the excess solid sinks to the bottom. So essentially keep adding the excess solid until that starts sinking to the bottom. Filter out any excess solid, leaving the salt water, then evaporate some water, and then leave the rest to evaporate slowly. Now we've got the pH scale, which is always fun. So acids produce H+ ions, and alkalis produce hydroxide ions, so OH-, in an aqueous solution. The pH scale, ranging from 0 to 14, measures the acidity of a solution, measured using a universal indicator of a pH probe. A pH of 7 shows that the solution is neutral, less than 7 is acidic, and more than 7 is alkaline. And you can see the ionic equation for neutralization there with H+ plus OH- gives you water. And there's just a nice little colourful scale. This is how the colours will represent with the indicator. So the most acidic is red, and then the most alkaline is very dark, like purpley blue. Then we have the experiment of titration. So this is used to calculate the volumes of acid and alkali solutions that react with each other. So you've got a little demonstration image here. This is really important. You may be asked to draw this. You'll need to know the names of the actual equipment. And how you're going to carry it out is you're going to wash the burette with using dilute hydrochloric acid and then water. Fill the burette to 100 centimetres cubed with acid with the meniscus base on the 100 centimetres cube line. So the meniscus base is like the little kind of dip in how the solution looks in it. Like you can kind of see in the little drawing how it kind of curves down. You want the base of that on the line. Then use 25 centimetre cube pipette to add 25 centimetre cube of alkali into a conical flask, drawing alkali into the pipette using a pipette filler. Add a few drops of a suitable indicator to the conical flask. Obviously this will depend on what your school uses. So whatever example you use, please make sure it's one that you are familiar with and not some kind of random term that's on this presentation then we are going to add acid from the burette to the alkali until endpoint is reached, as shown by the indicator. So essentially, we want to find a middle ground. You'll know with whatever indicator you are using at school what colour that needs to be, and it's different depending on what indicator you use. Then the volume acid needed to exactly neutralise the acid is the difference between the first 100 centimetre cube and second readings on the burette. Then repeat to gain more precise results. So essentially the difference in liquid between at the start with the 100 centimetre cube to where you're left at the bottom until you reach that end point is how much acid is required to neutralise. An example titration question here, so 25 centimetre cube of dilute hydrochloric acid is neutralised by 20 centimetre cubed of 0.5 mole per decimetre cubed sodium hydroxide. What is the concentration of the hydrochloric acid? So this is going back to the previous presentation where we looked at the kind of equations for moles and things. So you want to convert the volume into decimetre cubed. So this is really important. You need to make sure the units are in decimetre cubed before you even try and do any of the other equations. So to do this, to go from centimetre cubed to decimetre cubed, you just need to divide the number by 1,000. As you can see, has been done here in step 1. Then you want to work out the moles of NaOH moles. So moles is volume times concentration, so 0.02 times by 0.5, giving you 0.01. Then work out the mole ratio from the equation. So as you can see here, it's a 1-to-1 ratio, so the moles of NaOH equals the moles of HCl, so the HCl moles is 0.01. And then you can work out the concentration from there. So concentration is moles divided by volume. So the concentration of HCl is 0.4 moles per decimetre cubed. So the thing, apologies, that is 0.4 moles decimetre cubed, not per. And that's a really key difference. That is the difference between losing the marks, whether you have that slash and the minus there or not. But yeah, so that's kind of how you'd work your way through an example question like that. Again, I will at some point be going through actual exam questions and working them with you. But moving on to strong and weak acids. So strong acid is completely ionized by aqueous solutions. So an example is hydrochloric acid, whereas a weak acid is partially ionized in aqueous solutions, so citric acid. The stronger an acid, the lower the pH, and as pH decreases by 1 unit, the H+ concentration of the solution increases by a factor of 10. Strong and weak, however, is not the same as concentrated and dilute. This is a key difference. You need to make sure that you don't get this confused. Dilute is the amount of substance in a given volume, and concentration or concentrated refers to the H+ concentration in aqueous solutions. This is not the same as weak and strong acids. Then we have electrolysis. So the process of electrolysis is when an ionic substance is melted or dissolved. The ions are free to move about within the solution. Passing a current through substances that are molten or solution means that the solution can be broken down into elements. Oh my god, that's a terrible spelling error. And that's meant to say and. The substance being broken down is known as the electrolyte. Positively charged ions move to the negative electrode, which is also known as the cathode, and negatively charged ions move to the positive electrode, also known as the anode. And then ions are discharged at the electrodes, producing elements. When a simple ionic compound is electrolyzed in the molten state using inert electrodes, the metal is produced at the cathode, and the non-metal is produced at the anode, due to their ionic charges. And remember, we looked at the reactivity series here, so you can see the only things being going through electrolysis to be extracted is anything that's more reactive than carbon. So aluminium, magnesium, calcium, sodium, potassium in this case. Then looking a little bit further, so metals are more reactive than carbon. So 2-reactive can be extracted by reduction with carbon. That sentence doesn't even make sense. Metals are more reactive than carbon, so 2-reactive to be extracted by reduction with carbon. Again, like I just demonstrated or like showed you with the reactivity table or series, extracted by electrolysis of molten compounds. Large amounts of energy are used in the extraction process to melt the compounds and to produce the electrical current. Aluminium is fractured by the electrolysis of a molten mixture of aluminium oxide and cryolite using carbon as the positive electrode. This is because aluminium oxide has a very high melting point, so it would be too expensive to melt, hence why it's mixed with cryolite. And the positive electrodes need to be continually replaced because oxygen is formed, which means that with the carbon of the anode forming carbon dioxide, and it will just gradually burn away. Metals that react with carbon can be extracted by electrolysis as well. Then for our final slide, when it comes to the electrolysis of aqueous solutions, so the ions are discharged when an aqueous solution is electrolyzed using inert electrodes depending on the relative reactivity of the elements involved. At the cathode, hydrogen is produced unless the metal is less reactive than hydrogen, so more reactive ions want to stay within the solution. So this is really, really key. This is why it's so important to actually know and remember the reactivity series, because it influences so much. At the anode, if OH- and halide ions are present, so this is chlorine, bromine, and iodine, then one of the halide ions will be produced. If not present, then oxygen is formed. This happens because in the aqueous solution, water molecules break down, producing H+ and OH- ions that are discharged. And again, when representing the reactions that take place at the electrodes, we use half equations. So these are the same as the reduction and oxidation ones, but you can see here that it's referring to the anode and the cathode. So that is everything for today. Please, of course, let me know if you have any questions. Please put them below, and I will get back to you as soon as possible, or potentially your fellow students will get there before me. But yeah, I hope you enjoyed, and again, please feel free to subscribe, comment, and I shall see you soon.